Good morning. We are going to continue with Module 4, Work and Power. Now we're looking at the second unit, Work Calculation. You have here the 6 sections that we are going to study, which are 6 particular cases, which are the most common ones we are going to find. The definition of work prior to all this is the one we are looking at here. We gave it in the previous unit, and remember that it is quite complex in concept. Beyond our knowledge and what we are going to provide here, in terms of general calculus, is what is called a curvilinear integral. So what we are going to do is learn some particular cases, which are the ones that we usually use and that are the ones that we will have to know how to handle. We begin with one that is the most obvious of all. What happens when the force is 0? That is to say, no force acts. None acts because it does not exist or because it does exist. But during a certain section, the section AB, it turns out that it is not doing anything. In that case, if there is no force, the integral is quite obvious. The force is 0. 0 times differential of r gives 0, and an integral of zeros is 0. Therefore, if a force is 0, obviously it does not work. Logically, neither helps nor hinders the displacement. The second important particular case that we are going to see is this. A constant force in any trajectory. I emphasize constant force. I am not talking about the modulus being constant, but the whole vector. All the time we have the same modulus, the same direction, the same sense as it appears in the image on the left. In that case, although this integral is of a type that you will not have learned to handle, it happens as with all the integrals. If something is constant, we can take it out of the integral, in this case, f. So I have f for the differential integral of r. That is what becomes the sum of all the small displacements, one after the other, which is neither more nor less than the vector that goes from point A to point B. This is already an important result. Let us take into account, therefore, that the work is the constant force per vector that goes from the starting point to the destination point, and that if we realize, therefore, the trajectory does not influence. If instead of going along the path painted in green, we had gone from A to B by another path, it would have given me the same result. Beware. This happens with a constant force. It is not a general property. In the case that we have a straight path and a constant force, we have a particular case, as I say, of the previous one. But it has some specific formulas that are quite frequent. In this case, we have, as I say, that the work is forced by the vector AB. As all scalar points, that is modulus of the first, f without arrow, modulus of the second, the distance between points A and B, as shown in the figure, by the cosine of the angle they form, which would be the one you are seeing represented here. Well, developing a little, changing the cosine so that it is multiplied by f by virtue of the associative property of multiplication, we can see that f cosine of theta is precisely the value of the tangent force. That is, the modulus of the hypotenuse times the cosine of this angle is the adjoining leg, which would be the tangent force. Therefore, I am left with this formula for the case of, I repeat, straight trajectories, the tangent force times the displacement. Remember that the tangential component, as we saw in the previous unit, has signs. If it is in the same direction as the displacement, it is positive. If it is in the opposite direction, negative. Therefore, if the tangent force goes in the same direction as the movement, it helps the displacement. If it goes in the opposite direction, it is hindering it. Obviously, if the force were perpendicular, we would have that the tangent component is 0, and the work would also be 0. Although in this case we will talk more in general in the next slide. We have here 2 particular cases of the particular that are also of very common use. What happens if the force is precisely parallel to the trajectory? If it is like the first case, the one we have here represented, the tangent force would be precisely the modulus of f. If it is like in this case, the tangent force is less f, because remember that when going in the opposite direction to the trajectory, we must take a negative sign, and these expressions remain. If the force is in the same direction as the displacement, the work is f times d, perhaps the best known formula, but I repeat, it is only a particular case. If it is in the opposite direction, the work is minus the modulus of the force times the distance traveled. If the force is normal to the path, we have already seen in the case of the straight line that it was 0. In fact, it is general. For any path with any shape, if the force is at all times perpendicular to the path itself, as we see in the image on the left, it will turn out that the development leads to the following result in the scalar product. modulus of the first vector times modulus of the second times cosine of an angle that is continuously 90 degrees, and as the cosine of 90 degrees is 0, I will make an integral of zeros in any case, therefore the work will be 0. In short, the work of a force normal to the path is always 0, which should be obvious since it neither helps nor hinders that displacement. Another particular case, a force of constant modulus and tangent to the trajectory, not to be confused with the previous view of constant force. Here the modulus is constant. We can see that the direction is not, and neither is the direction. In addition, that direction is all the time tangent to the trajectory, as we see in the figure. In this case, making the development, I am left that the angle that forms f differential of r is at all times 0 degrees, whose cosine is unity. Therefore, I am left with the integral of f times differential of r, and f, since it is the modulus and the modulus is constant, I can take it out of the integral. I am left with f times the integral of differential of r. Be careful, it is not like a case seen before where I was integrating differential of r vector. Now I am integrating differential of r measure, and therefore the sum of the measures, which is what an integral is the total length of the curve. So I am left with the work, in this case is the modulus of the force, times the length of the curve of the path traveled. I repeat, not the straight line distance, the length of the curve. As I did below, be careful that work is minus f times L if the force has a direction against displacement. This is because in that case, if the force was not as we see in the figure, but always the other way around, the angle it would form with the differential of r would not be 0 degrees, but 180, and the cosine of 180 is minus 1. Therefore, the development we have above would be exactly valid. But with a minus sign at the end, as I did here, it would be minus the modulus of the force times the length traveled. The last case we are going to see, the most complex of all the ones we are going to analyze here, is when the force has variable modulus and is parallel to a straight path. As we see here, we see that the force changes its modulus, but it is always oriented exactly the same as the trajectory, which in turn is straight. In that case, the development leads us to this expression, f times differential of r times cosine of 0 degrees. Since we know that the cosine of 0 is 1, I will be left with the integral of f times differential of r. And now we make a point. Let's place or imagine a coordinate system with the x-axis placed precisely on the trajectory, so that the modulus of the force will be a function of x. In this case, differential of r would be precisely differential of x. So I would be left with this expression. Therefore, if I have the force modulus as a function of the position x, I only have to do the integral of that force and I would have precisely the work. Be careful. Do not confuse this with a concept seen in the unit in the previous topic, which was that of mechanical impulse. In that case, it was force multiplied by time differential. Here I am talking about force times x differential. Finally, here is a summary of what we have seen. In cases where the force is 0 or normal to the trajectory, the work is 0. If the force is constant, the work is the force vector scalarly multiplied times the vector AB, which goes from the origin to the end. If the path is straight, it is abbreviated, and I am left with tangent force times distance traveled, with all the particular cases of f times d and minus f times d, when it is also in the same direction or in the opposite direction to the path. If the force is of constant modulus and tangent to the path, the work is force times the path length, or minus f by L if it were in the opposite direction. And finally, the formula of the integral that we have just discussed in the case of variable modulus and parallel to straight path. We can say that we are not going to use in the following topics, nor in the examples, any of the integrals, or the integral as a general concept. Everything that we are going to develop in the following units will refer to applications of these particular cases that we have summarized in this slide. And with that, we finish the second unit of the present module.